Alright, welcome back. So, last time we went through creating our command pools, the command buffer, and recording commands. Yeah, so that was pretty interesting. Saw how we can actually issue commands and how they can put into specific queues. And now we are done with that. So we're going to move on to rendering and presentation, which is hopefully going to be the cool bit where we see some stuff that isn't just code. Okay, so in this chapter, this is chapter where everything comes together. We're going to write the draw frame function that will be called from the main loop and put the triangle on the screen. Yes, finally. Let's start by creating the function and call it from within the main loop. All right, so back up to the top. Computer's done that thing again. Bear with while I do accessibility and reset my what was it? Repeat keys. Just turn it off and on. Just have to do that every now and then. Okay, so back down here. Void, it's almost certainly going to take our app. So let's keep that going. Main loop, that's what we're calling it. And looks like it's just after the poll events. So draw frame. And yep, passing up the app. And then let's go down to, not here, let's go to create instance, where are we? Create surface, pick device, create swap chain, keep going. Create graphics pipeline. Okay, here's the more utility type functions. Actually, that's just one really massive create pipeline function. Frame buffer is record buffer, create command pool. Okay, here we go. Let's do it here. All right, outline of a frame. At a high level, rendering a frame in Vulkan consists of a common set of steps. Wait for the previous frame to finish, acquire an image from the swap chain, record a command buffer which draws the scene onto the image, submit the recorded command buffer, and present the swap chain image. While we will expand the drawing function in later chapters, for now, this is the core of the rendering loop. Synchronization. The core design philosophy in Vulkan is that synchronization of execution on the GPU is explicit. The order of operations is up to us to define using various synchronization primitives, which tell the driver which order it wants things to run in. This means that many Vulkan API calls which start executing work on the GPU are asynchronous. The function will return before the operation is finished. Okay. Okay, so when we call a GPU type function, the response might come before the thing's actually happened. Fair enough. In this chapter, there are a number of events that we need to order explicitly because they happen on the GPU, such as acquire an image from the swap chain, execute commands that draw onto the acquired image, present that image to the screen for presentation, returning to the swap chain. Okay, each of these events is set in motion using a single function call, but are all executed asynchronously. The function calls will return before the operation is actually finished, and the order of execution is also undefined. That is unfortunate because each of the operations depends on the previous one finishing. Thus, we need to explore which primitives we can use to achieve the desired ordering. Semaphores! That's a pretty common concept in other areas of programming. So it's basically flags to say do stuff or don't do stuff. And then the thing that we want to wait on sets the flag so the following items can continue their execution. I won't go into that because that's just a bit of pseudocode that doesn't actually do much. Note that in this code snippet, both calls to VK. Okay, fine. Fences. A fence is a similar purpose, has a similar purpose, in that it is used to synchronize execution, but it is for the ordering of execution on the CPU, otherwise known as the host. Simply put, if the host needs to know when the GPU has finished something, we use a fence. Similar to semaphores, fences are either in a signaled or unsignaled state. Wherever we submit work to execute, we can attach a fence to that work. When the work is finished, the fence will be signaled then we can make the host wait for the fence to be signaled or unsignaled, guaranteeing that the work has finished before the host continues. A concrete example is, let's ignore that. Unlike the semaphore example, the above code does block host execution. This means that the host won't do anything except wait until execution is finished. For this case, we had to make sure that the transfer, okay, that was using a file, like taking a screenshot and saving it to disk. The screenshot being done on the GPU, CPU has to wait around to get that screenshot. Okay, blah, blah, blah. The case, yeah, in general, it is preferable to not block the host unless necessary. Yep, that makes sense. We want to feed the GPU and the host with useful work to do. Waiting on fences to signal is not useful work. Thus, we prefer semaphores or other synchronization primitives not yet covered to synchronize our work. Fences must be reset manually to put them back into the unsignaled state. This is useful. Okay, so in our code, we have to manually set it to be unsignaled. This is because fences are used to control the execution of the host, and so the host gets to decide when to reset the fence. That's your running application. Okay. Contrast this to semaphores, which are used to auto work on the GPU without the host being involved. In summary, semaphores are used to specify the execution order of operations on the GPU, while fences are used to keep the CPU and GPU in sync with each other. What to choose? We have two synchronization primitives to use and conveniently two places to apply synchronization: swap chain operations and waiting for the previous frame to finish. That's one. We want to use semaphores for swap chain operations because they happen on the GPU. Thus, we don't want to make the host wait around for it if we can help it. For waiting on the previous frame to finish, we want to use fences for the opposite reason, because we need the host to wait. All right. This is so we don't draw more than one frame at a time, because we re-record the command. Yeah, so if we try and do a second frame, we'll overwrite the frame buffer, the command buffer, while the GPU is busy using it. So we could create undefined behavior. That makes sense. Creating synchronization objects, we'll need one semaphore to signal that an image has been acquired from the swap chain and is ready for rendering. Another one to signal that the rendering has finished and presentation can happen. And a fence to make sure that only one frame is rendering at a time. Create these three objects on your app. Doesn't really say that, but you know what I mean. All right, and create the semaphores. We'll add the create function for this part of the tutorial. Okay, and it's going to be create, in the init Vulkan function. But we're going to have to create the prototype first. Put it here. So void. It's going to take a p app, or not that. It's going to take an app. Point to the p app. All right, and then in our init Vulkan, in the actual function call, which is down here. Oh, didn't mean to bring all that along with me. Okay, and then after the create command buffer function, I think create command. All right, so just above here. Whoops. Okay, creating semaphores requires filling in the VK semaphore create info struct, of course. But in the current version of the API, it doesn't actually have any required field besides S-type. Oh, that's new. Okay. I like how it's quite a new thing. We can grow along with it. Future versions of the Vulkan API or extensions may add functionality for the flags and the pnex parameters, but hey, not just yet. Creating a fence requires filling in the fence create info, alright, which is similarly new by the looks of it. As in, doesn't really require much. Familiar pattern. Let's copy this. So this is our error checking when we're creating our bits. P app device. There's our semaphore info and a null pointer, or just straight up null. Image available semaphore. Oh, that's also an IP app. If that doesn't equal success. Or I would kind of like to split these out actually. I'm going to split them out because I prefer to know exactly what's having problems. If this has an issue, then we'll bail as well. And finally, if this has an issue, we shall similarly bail. And we're going to exit with, oh, I think we've done 13, haven't we? We certainly have. This time it's 14. We haven't done that. We have. We've done 15? No. Alright, 15 at B. All that. Okay. And we're going to say, failed to create fence. Failed to create semaphore. I'm going to actually say what the type of semaphore it is. Just because why wouldn't you? Make life easier for myself later on. Okay. The semaphores and fences should be cleaned up at the end of the program. Alright, that makes sense. Then when all commands have finished and no more synchronization is necessary. Alright, so in the cleanup, VK destroy semaphore. As a device, there's the P app image available semaphore, and then just null after that. And then the other semaphore, which is render finish semaphore, and our VK destroy fence. Oh, music's kind of struggling for me. And that is in flight fence. Alright, bear with. Excuse me. Okay, so moving on to the main drawing function, waiting for the previous frame. At the start of the frame, we want to wait until the previous frame has finished, so that the command buffer and semaphore are available to use. To do that, we call VK wait for fences in our draw function. Okay, VK wait for fences, thanks. I'll pass in our device and the number 1, because I'm assuming there's only one fence. P app in flight fence and VK true and this. Okay. VK true and this, which I think in C we have to C language. I think we have to include the header for that, a specific header, like I think it's called limits or something. Value of, what is the value of that? Yes. I don't really want to know what the value is. Or you could not take me back to Google, that's fine. I'm pretty sure. Oh, yeah, they were limits. I knew I'd read it somewhere once upon a time. This is C++. Yeah, there you go. So we need to include that. Alright, you're in 64 max. Oh, I've already got it. Huh. Wonder why I already had that. I don't remember doing that, fair enough. Okay. The wait for fences function takes an array of fences, yep, and waits on the host. The VK true we pass here to indicate that we want to wait for all fences. Oh, okay, because we're passing an array of fences. Well, kind of. But in the case of a single one, it doesn't matter. Alright. This function also has a timeout parameter that we set to a maximum value of 64-bit unsigned integer, which effectively disables the timeout. After waiting, we need to manually reset the fence to use unsignaled state with the reset fences call. Okay, vk reset fences, passing in a p app device again, and the number 1 and our pointer to p app in flight fence. Before we can proceed, there is a slight hiccup in our design. On the first frame call to draw frame, which immediately waits for the in-flight fence, so it's never going to be signaled because we haven't got anything to signal it. In-flight fence is only signaled after a frame has finished rendering. Yet, since this is the first frame, there are no previous frames in which to signal the fence. Thus, wait for fences blocks indefinitely. Yes. There are many solutions to this dilemma. There's a clever workaround built into the API. Create the fence in the signal state so that the first call to vk wait fences returns immediately since the fence is already signaled. Excellent. Okay, so to do this, we add the vk fence create signal bit flag to the vk fence create info, which is here. All right. So the flags, I thought we weren't going to set flags. Oh, that was in the semaphore. vk fence create signaled bit. Great. Acquiring an image from the swap chain. The next thing we need to do is we need in the draw frame function is to acquire an image from the swap chain. Recall that the swap chain is an extension feature, so we must use the function with the vk star khr naming convention. All right, so in our draw frame, which is here, after we've awaited and reset, then we are likely doing this. P app, our swap chain, this max, which is probably disables the timeout, and image available semaphore is also on our app, and that's probably everything. Image index. Now then, what is that? In the scope of this function, okay. Yes, this is the current swap chain image view index. That's what it is. First two parameters of that function, the acquire next image, are the logical device and the swap chain from which we wish to acquire an image. The third parameter specifies a timeout in nanoseconds, which we're basically disabling it. The next two parameters specify synchronization objects that will be used to signal when we in the presentation engine is finished using the image. That's the point in time where we want to start drawing into it. It is possible to specify a semaphore, fence, or both. We're going to use our image available semaphore for that purpose here. The last parameter specifies a variable to output the index of the swap chain image that okay. So that is keeping track of where we are in the list of images in the swap chain. Recording the command buffer. With the image index specifying the swap chain image to be used, we now need to record the command buffer. First, we call vk reset command buffer on the command buffer to make sure that we're able to record. Okay. vk reset command buffer on our p-app command buffer, passing in 0. The second parameter for the buffer is the command buffer reset flight bits flag. Since we don't want to use anything special, we leave it at 0. Now call the function record frame buffer to record the commands we want. I can hear ghosts in my house. weird noises. Okay, we are missing something from our call to command buffer. Takes in an app first. That'll be why. There you go. Right, now submitting the command buffer. Queue submission and synchronization is configured through parameters in the VK submit infrastructure. Oh, there's a lot going on here. All right. Carrying on. Building our struct, and then p-app for our available semaphore, image available semaphore. I like to do that. Wait stages and the wait semaphores. Okay. Yep, that all looks good. Excuse me. The first three parameters specify which semaphores to wait on before execution begins, and in which stages of the pipeline to wait. Okay. That's quite a nice way of doing it. Okay. We want to wait with writing colors to the image until it's available, so we're specifying the stage for the graphics pipeline that writes to the color attachment. That means that theoretically the implementation can already start executing our vertex shader and such while the image is not yet available. Oh, cool. Each entry in the wait stages array corresponds to the semaphore with the same index in p wait semaphores. Yeah. Okay, excellent. Then we also need to add these two. The next two parameters specify which command buffers to actually submit for execution. We simply submit the single command buffer we have. Yep, that makes sense. The app for our command buffers. And then this new structure, the signal semaphore count and p signal semaphores. Parameters specify which semaphores to signal once the command buffers have finished execution. In our case, we're using the render finish semaphore, which we created. All right, cool. So that is our p-app render semaphore. We can now submit the command buffer to the graphics queue using vk submit. The function takes an array of vk submit info structure, and because you can send multiple, you can submit multiple things at once. Okay. The last parameter references the optional fence that will be signaled. Yeah, okay, and the command buffers which execution. This allows you blah blah blah. So we have that in-flight fence to say, hey, there's already something going on. Wait up. So let's, nearly forgot to do that. The actual submission. Printf. In our earlier functions, I forgot to do my null terminators, which I guess is easy to do. Luckily, I remember just then. P up. And our queue. Yeah, that's right. And we probably want to exit out here as well. So exit with 16. Not there, over there. Otherwise, you'll never see the print. Okay, subpass dependencies. Oh, is that a Mozzie? It is. Oh, I never cut you. I did. Good on you, Australia. Remember that the subpasses in a render pass automatically take care of the image layout transitions. These transitions are controlled by subpass dependencies, which specify memory and execution dependencies between subpasses. We have only a single subpass right now, but the operations right before and right after this subpass also count as implicit subpasses. Okay. I wonder if that's if you have two subpasses, do you have one either side? Or is it like three? Or just the two? There are two built-in dependencies that take care of the transition at the start of the render pass and at the end of the render pass, but the former does not occur at the right time. It assumes that the transition occurs at the start of the pipeline, but we haven't acquired the image yet at this point. There are two ways to deal with this problem. We could change the wait stage for the available semaphore to VK pipeline stage top of pipe bit to ensure that okay, so that knows the start. Okay. Or we can make the render pass wait for the VK pipeline stage color attachment output bit stage. I've decided to go with the second option here because it's a good excuse to have a look at the subpass stage. I mean, subpass dependencies and how they work. Fair enough. Subpass dependencies are specified in the VK subpass dependency struct. Go to the create render pass function and let's do some updates. We'll get there eventually. And add this one. Okay, we've got a dependency. Where are we adding that to? The first two fields specify the indices of the dependency and the dependent subpass. The special value of VK subpass external refers to the implicit subpass before or after the render pass, depending on whether it is specified as source subpass or destination subpass. The index 0 refers to our subpass, which is the first and only subpass. The destination subpass must always be higher than the source subpass to prevent cycles in the dependency graph. Yeah, okay. Unless one of the semaphores is VK subpass external. So, okay, adding more things to our dependencies. Need to field specify operation. Okay, stage mask and axis mask. This can be accomplished. Okay, that's fine. Next. The operations that should wait on this are the color attachment stage and involve the writing of the color attachment. These settings will prevent the transition from happening until it actually is necessary. Okay, moving on again. Render pass. Oh, so now we need to add these two to our render pass info. So really, this should be here. Oops, not all that. That was too much. Let's put it there. All right. Okay, the VK subpass create infrastructure has, yes, we already added that, okay. Now on to presentation. The last step of drawing a frame is submitting the result back to the swap chain to have it eventually show up on the screen. Presentation is configured through the VK present info KHR structure at the end of the draw frame function. So back to our draw frame. So at the end of that, we need to throw this in. Okay, so once we present it to the queue, submitted it to the queue, we create this present info struct. The first two parameters specify which semaphores to wait on before presentation can happen, just like the VK submit info. Since you want to wait on the command buffer to finish execution, thus our triangle being drawn, we take the semaphores which will be signaled and wait on them. This is what we use signal semaphore for. Cool. The next two parameters specify the swap chains to present images to and the index of the image for each swap chain. This will almost always be a single one. Alright. The app swap chain. Excellent, we're getting closer. And this is an optional for our present info, which is, there's one last option for the parameter called pResult. It allows you to specify an array of VK result values. Okay, to check for every individual swap chain. Okay, so we can run through and see which ones aren't working. It's not necessary if you're only using a single swap chain like we are, because you can simply use a return value. Okay, that's fine. I'll put it in as null. Okay, now let's call this function, which is our present function. The VKQ present KHR function submits the request to present an image to the subchain. We'll add error handling for both the acquire and present in the next chapter, because their failure does not necessarily mean that the program should terminate, unlike the functions we've seen so far. If you did everything correctly up to this point, then you should now see something resembling the following when you run the program. Oh God, I hope so. Okay. P-app. Righto. Build and game. It didn't work. Bummer. Okay, let's see how far we get without trying to actually draw. Oh, we get quite a few errors, or warnings anyway. And we cannot quit our app. What have we got here? That's just naming what the struct is. So this semaphore is signaling VKQ. That was previously signaled to VKQ, but has not since been waited on by any queue. Okay, so it's signaling a semaphore, but it's not being waited on by any queue. What queue is it? How do we find that out? Object type, that's just references. It's just like, I think just memory addresses. We don't know what the actual queue is. It looks like we've got 2 of those, and then a third one of application has already previously acquired 3 images from the subchain. Only 3 are available to acquire using the timeout of VK. Given that the subchain has 5 and the VK surface capabilities is 3, the Vulkan spec states that if the number of currently acquired images is greater than the difference between the number of images and the subchain, and the value of the minimum. Okay, so the number in the subchain is 5, the value of the minimum is 3. So the difference is the same. Then the timeout must not be this maximum. And then it looks like we have the same one again. Is returned by the... Oh, what's this one? Previously acquired 4 images subchain. That's saying the same sort of thing. VK get physical device service capabilities. Let's have a look at where we're using that. VK device get capabilities. Alright. I have a feeling it's something to do with queues, because it says it's something to do with queues. So it looks like we are trying to... Oh, that's only error because I stopped using it. We're trying to wait on a queue. What was the wording? Has not since been waited on by any queue. So a semaphore hasn't been waited on by any queue. I don't really know what that means. Let's go to all the places where we play around with the queues. Alright, our queues are also, what type of queues? VK queues. That's these, the graphics and the present queue. Okay. Now, come on, you've definitely used graphics queue before. We are... So what's this one? Get family device, yep, that's right. Oh, we've got a little error for unused variable here. May as well ditch that. And then get family device. Just call down here, we're not using these device features. Alright. Where else are we looking at these. There's more. VK get device Q. So when we create a logical device, we get our family indices up here. Okay, the features, we create our 2 queues. Get family device queues. Yep, that populates the queues with the indices. And we create info. This is just changing the struct depending on validation layers. Then we create the actual physical device with the create info, which contains our queues. And then what's this function? VK get device queue. What does that do? And why is it only on the graphics family? The graphics queue. Are we calling that anywhere else? No. Let's try and find it in here. 2, I don't know what the 2 means. Get a queue handle from a device. Oh. Okay, so we pass the device, pass the family index from our indices up here. And then the queue index, which would be 0. And then the actual queue, which is our graphics queue. So why don't we, maybe I missed something. Maybe we need to do that for the other queue as well. Present family, and then is the index going to be 1? Present queue. I need to look this up to see if I missed something. Queues. Where's our queues? Oh, it was ages ago. If I stuff this up. Oh no. We can use the VK function to retrieve the queue handle for each family queue. But we're only doing the graphics one. Did I miss the second one? I did. There is also a present. But where does that go? Let's look at the C++ code. Right next to each other. Oh, index is 0, mind. So yes, I stuffed up. At least I stuffed up one thing. Let's see if that helps. We still get lots of errors. And we can't quit. This is not weird since it's on a queue. Interesting. Well, that's funny that I would have messed that up. Oops. Am I updating this properly? Or do I need to use those actual indices rather than this? I wonder. Nope. Still bugged. Cryptic errors. Especially if you're not really that familiar with Vulkan. The Vulkan spec states that so maybe the number, the image index we're passing around, maybe that's not correct. Interesting. Okay, let's put that back to what it was, and then Let's go back down to the draw function, draw frame. There must be something else we're missing, so let's think about this. Oh. No, we still don't get to this stage. This is talking about potential errors, but remember that all of the operations in the draw frame are asynchronous. That means that we need to exit the main loop. Okay. I doubt this is going to help us, but let's just do it anyway. Main loop. Outside of there. On our P app device. Then back to our draw frame. Let's just do it once more with feeling and see what happens when we run. Ooh. Oh, that's interesting. It works. So when presenting, does that mean that we were never signaling? It does. Because we weren't presenting, we were submitting to the recording the buffer, but we never actually returned or signaled the semaphore, or maybe the fence. That makes sense. Okay, check it out. We've got, can't resize it, but you can quit it. No, you can't. Why can't you quit it? Oh, you can. I think if you use the right keys. Yeah, there you go. Hey! Alright, that's excellent. Let's have a look at that one more time. Because it's so pretty. Ooh, could do some anti-aliasing on that. Alright, excellent. So we've done that. You can also wait for operations to specify command Q to be finished with the await idle. These functions can be used as a very rudimentary way to perform synchronization. You'll see that in the program that now exists without problems when closing the window. Sweet. Conclusion. A little over 900 lines. Really? Let's see what we actually have. What if we do like clock? And then we do like, I think specifically, no. Let's do L for all files. Does that work? No. What we do C and then the main C? I don't remember how you use clock. Oh, I think it's just like you clock and then that. Yeah, there you go. So our C file is indeed 904 lines of code. A good amount of markdown. Some JSON. Don't remember doing any JSON. GLSL shader stuff. Make and Born shell. Born supremacy. Alright, cool. A little over 900 lines of code later, we've finally gotten to the stage of seeing something pop up on the screen. Bootstrapping a Vulkan program is definitely a lot of work, but the takeaway message is that Vulkan gives you an immense amount of control through its explicitness. I recommend you to take some time now to reread the code and build a mental model of the purpose of all of the Vulkan objects in the program and how they relate to each other. We'll be building on top of that knowledge to extend the functionality of the program from this point on. Keeps on going, cool. The next chapter will expand on the rendering loop and handle multiple frames in flight. Excellent. We got there, sort of. Get status, actually I already know what it is. Get add main, and don't add that. Git commit, rendering and renders and presents the triangle. Git push origin main. Excellent. We made it to the sort of end where we at least have a working triangle. I think I might do more videos on the rest of it. But for now, thanks for watching me struggle through it. Catch you next time.